Okay, quiz 14.4 on reaction mechanisms and catalysis. So let's look at question 1. It concerns this reaction, the decomposition of ozone. We're given a balanced reaction and an enthalpy of reaction and the following proposed mechanism. Notice this has a fast pre-equilibrium and then a slow second step. And let's just work our way through these questions. Does this mechanism add up to the total overall reaction? So let's add up everything that's on the left side of both steps in the mechanism. We'll have O3 plus O plus O3. And on the right side, we'll get O2 plus O plus 2O2. So that O can cancel out, and we're left with 2O3 yields 3O2, which is indeed the overall reaction. So we're safe there. Identify any catalysts or intermediates in the reaction. There are no catalysts, but that oxygen that got canceled out. If we look at the mechanism, we see that it is first produced in the second step. Hold up. First produced in the second step, in the first step. Oh, that's produced in the first step, and then consumed in the second step. So that would make oxygen an intermediate. Give the molecularity and the rate law for each elementary step, including the reverse reaction in step 1. So, let me erase this. We'll have rate 1. This is a unimolecular process because we just have the one ozone there. So that's going to be K1O3, unimolecular. And then we've got rate -1. That's going to be K-1 and O2O. That's a bimolecular process. These two have to find each other in order to combine in the reverse reaction and generate O3. And then rate 2 is going to be K2, put the rate constant in front, O and O3. And that is a bimolecular process. So what does this reaction mechanism predict for an overall rate law? Well, step 2 is the slow step, so this kind of is the predicted rate law, but we have a problem. Oxygen is an intermediate. We cannot measure nor control the concentration of oxygen, so it's really useless for us in terms of the rate law. But because that first step reaches an equilibrium, we can say that rate -1 is equal to rate 1. Right? The reverse rate and the forward rate are equal to each other. And what's rate -1? That would be K-1 O2O. And what is rate 1? That would be K1 O3. And so we can solve for the concentration of that oxygen. It's going to equal K1 over K-1 O3 over O2. And we can go ahead and plug that in to our O in the overall rate law. And what we'll end up with is that the overall rate is equal to the observed K, which is K2, K1 over K-1, times the concentration of O3 squared, because this O3 combines with that O3, divided by the concentration of O2, which comes from there. this is the overall rate law. And this is actually a really interesting rate law because you'll notice what we have is something in the denominator. We've never seen that before now. We could call this something like negative first order or inverse first order kinetics. Basically, the more product you have, the more oxygen you have, that will inhibit and slow down the reaction. It's an interesting result of this particular reaction mechanism. Okay, and draw a plausible reaction coordinate diagram. So, let me erase some space here. So in order to be plausible, we need to include a couple of particular elements. We'll have H on this axis and the reaction coordinate on the other axis. And I want to give myself a little bit more room. Okay, so we know that the enthalpy of reaction is negative, so we'll have reactants higher than the products. We know that it is a two-step mechanism, so there will be two maxima overall. And the first step is an equilibrium step. So we'll draw this first step. It's fast, so it's a relatively low activation energy barrier. And because it's equilibrium, I'll make sure that the intermediates are relatively close to one another. And the second step is slow, so I'll give it a larger activation energy barrier down to the products. And I don't know if this is really how it looks as far as like actually how high these activation energy barriers are. All I really know is that this one is smaller than that one, that this overall reaction enthalpy should be exothermic, and that because it's in equilibrium, it's at least probable that this intermediate energy should be close to that initial energy. All right. So that is decomposition of ozone. Question 2 has to do with enzymes. And so S and P here stand for substrate and product. Substrate is whatever your biomolecule is that needs to react, and it'll go to products. And it actually doesn't matter. One or more products doesn't change the mechanism here. Now substrate going to product does not happen at a very fast rate without the help of a catalyst or an enzyme. And so enzymes follow this mechanism. It's called the Michaelis-Menten mechanism. And first, the substrate will bind with the enzyme. This is a fast process that reaches equilibrium. And then the enzyme-substrate complex will undergo a reaction where the substrate becomes products and breaks apart from the enzyme. So that doesn't look too bad. Let's answer the same questions above. So the first question, does it add up to the overall reaction? Let's figure out what the overall reaction is for this Michaelis-Menten mechanism. On the left side, we would have E plus S plus the ES complex. On the right side, we would have ES plus E plus P. And so we can get rid of ES, and we can get rid of E, and we're left with substrate to product. So it does add up. Do we have any catalysts or intermediates? Well, the things that got crossed out are our candidates. ES, the enzyme substrate complex, was first generated in step 1 and then consumed in step 2. That makes it an intermediate. E, the enzyme itself, was first consumed in step 1 and then regenerated in step 2. That makes it a catalyst. Okay, let's give the molecularity and the rate laws for each of the individual steps, including the reverse step. So rate 1 is going to equal K1 times your enzyme concentration and substrate concentration. Rate -1 is going to equal K -1 times the complex concentration. And rate 2 is going to equal K2 times the complex concentration. Now, this is bimolecular, and these are both unimolecular. And what is the predicted overall rate law? Well, step 2 is a slow step, so that is our predicted overall rate law, but it includes an intermediate, which is a problem. So we'll again look at how the reverse rate, rate -1, is equal to the forward rate in that first equilibrium step. And that means that K -1 ES is equal to K1 E times S. So ES is equal to K1 over K -1 ES. We just move that K -1 over there. And now we can put this quantity into our overall rate law. And we get that the overall rate is equal to K2 K1 over K -1. We could just call this the observed rate constant. Oh, sorry, you can't quite see that. We'll call that the observed rate constant, and end up with ES. So first order with respect to enzyme, first order with respect to substrate. And then lastly, we're going to draw a plausible reaction mechanism, a plausible reaction coordinate diagram. And it could look exactly like the last one. We're going to have an equilibrium in the first step that is fast, so we'll have a small hump and an intermediate similar in energy. We've got a slow second step, and it could be endothermic overall. So actually I'll just draw it right here. This is for an endothermic reaction, or it could be exothermic overall. And we don't really know. Enzymes catalyze all sorts of reactions. Some are endothermic, some are exothermic. And that's it for quiz 14.4.